ஆஃப் பண்றீங்களா? முன்னாடி முன்னாடி லைட். Okay, since we're already very late, why is this? It's kind of out of focus, huh? ஏன் அப்படி? இதுல இருந்து போய் அதில் வரலாம். Is anyway. Is this any better? Is this any better? This one is not good. Hello? Echo wherever. Anyway, so very briefly here, you can't see this anyway. So I've already sent an email, okay? So you have to review it. And if you want to make any changes to your paper assignment, you will have to quickly, you will have to come back to us, okay? Come back to me and then give a reason why, you want to change. And then, but I want the assignments to be finalized, okay? We're already at the end of the week, maybe by next Monday. So please do take some time to read the paper that has been assigned to you. And if for some reason, strong reason that you don't, you want another one, that you will have to propose that. Now, we've already kind of shortlisted the papers based on the topics, the content that we want to cover. So you may not get, some of the papers on the list. ஒருத்தருக்காக இது ஒரு பெரிய இது. இல்ல கரெக்டா தான் இருக்கு. ஹலோ, பண்ணிட்டேனே இதுலையா? ஹலோ, okay. Yeah, there will be some limited movements that you can do. I mean, maybe swapping would be possible. Yeah. And because most of the papers that we want to discuss on that list is being assigned. So, but anyway, we can work if indeed you have a strong desire to for a particular paper. Okay, so what I want to do today is, we only have an hour since I have to leave, or I can take the 6 p.m. if you're willing to go till 5:30. Okay, so okay, last time you had some question, okay, about the lecture. Towards the end of the lecture, you had a question and I had to rush to the thing. I mean, I don't know if you remember it, I'm willing to answer it, or you could ask again. Anyway, so what I want to cover today is, kind of what is inside a SAT solver. Okay, and Z3 is a SAT solver. It's actually a SMT solver because it supports other things. So suppose you are only working in the propositional domain. Okay, so then it's a Boolean SAT solver. Otherwise, it's an SMT solver. So I'm addressing what is in, what kind of things go on inside a SAT solver. Okay, so that is the thing. Now, so let me start with this. Okay. So this formula, okay, all this is satisfiable, okay, and this is unsatisfiable, and so is this. I think. In any case, there are some of them satisfiable and some of them unsatisfiable. Now let's go back. So a naive method for how would you solve it? You would make a truth table, okay, listing all possible assignments to the variables, and then you will check for each of them, whether it is satisfiable or not. So what is the disadvantage of that method? Anyone? Yes. In the worst case is 2 to the power n. And when does that happen? When you have to look at all 2 to the n, when it is unsatisfiable, then you will have to check each and everything. Now, if it is satisfiable, the best case would be when it is a tautology. So the moment you get, since it is true for every possible assignment, you will, the moment you check one, at least for checking satisfiability. Otherwise, the order in which you pick the assignments, okay? The disadvantage, as I said, that is one, okay? That's the main thing. But another thing is that it doesn't allow for partial assignments. Sometimes, even with partial assignments, by partial assignment, I mean assignments to only a subset of the variables, may make it go to true, because all the other assignments to other variables might be like don't care, okay, once you pick that. So those kinds of things are not possible, okay? So yeah, so what does kind of make a particular formula, proposition formula unsatisfiable? What could be the source? Because the unsatisfiability is the worst case thing. So you want to do. So in this case, for example, variables that today is not my day. For example, in this case, you could, by focusing your attention on things that variables that appear in opposing polarity in two different clauses might be helpful. Because, see, for example, if you have a formula in which every clause in which there is some variable that appears with a unique polarity, right? I mean, either exclusively positively or exclusively negatively, then it's always satisfiable because there's no conflict at all. So the real thing happens is when the same variable appears in differing polarity in one or in more than one clauses. Okay, so that's when you have a potential conflict. And if there is, some subset of clauses which are not consistent with either B or B, so then you will end up always having a conflict. Okay, and that's kind of the intuition. So the clauses will, potentially conflicting. So checking SAT in the worst case might require you to take a look at all possible subsets of the clauses in a formula in order to check whether there is a circular kind of conflict in that things. And that's why whenever you have to search for all possible subsets, there are exponential number of subsets of clauses. That is kind of an intuition. So one of the earliest methods that was devised to check, to get a decision procedure, for checking satisfiability or unsatisfiability was this resolution principle, okay, which concentrated on looking at these variables that appear in differing polarities, kind of eliminating one at a time, and see if you could either end up deriving a conflict or eliminating all of them. So in which case you'll be able to say that it is satisfiable. And that's what is resolution principle. Okay, and I think the reason that it is important for you to understand at the core of even modern day solvers, some variation of this principle is what is used. Okay, and that's why it'll be interesting to understand that. So what is resolution principle? This one rule is enough, doing repeatedly to check satisfiability or unsatisfiability. So given two clauses, okay, which have one variable appearing in conflicting polarity. Okay, so that's what. So two clauses. The other literals can be whatever they are. Then what it says is this C1 and C2, conjunction of this clause, is satisfiable whenever this resolvent, okay, which is just eliminates those C and C bar and takes the union of the rest of the literals, is satisfiable, correct? Because, you know, the way that you could, obviously, C cannot be involved in the satisfiability of this, because if C is 1, you know, all the other things being assigned to 0. So if you can see this, okay, so when you say that this is satisfiable, what I say is this one, whenever this is satisfiable, R, the resolvent, is also satisfiable. Okay, you understood how the resolvent is derived, right? You just eliminate C and C bar. And whenever this is unsat, this is also unsat. Okay, which means this is implied by C1 and C2. The resolvent is implied. They're not equivalent. Okay, they're not equivalent because this does not have the variable C at all. Okay, when are two Boolean formulas equivalent? When they evaluate to the same truth value for every possible assignments. Okay, so in this case, is it possible now? Keep going back to the thing. I don't know why this thing is not dead. There's something there that happens or what? No, see, that's what is being displayed. But that's whenever that probably goes into sleep, it will happen. So how can you? What do I have to do in mine? So what do I do here? Yeah, because this is here, I'm still settings off. Yeah, system preferences. I know. Nobody went back to this thing. So after this, I'll have to, okay, I have to type okay. Yeah. So they are, so this works. Yeah, so in this case, these two are meant to be equally satisfiable. Okay, whenever this is satisfiable, so will this be. Okay, and if this is unsatisfiable, so is this unsatisfiable. So when is this satisfiable? You can assign C to one, which is satisfiable. In which case, one of the B's have to be assigned to one. In which case, this is also satisfiable. But if you assign something C to 0, then this would be 1, in which case you will have to make one of the A's satisfiable. Therefore, this is satisfiable. Now, the only case in which this will be unsatisfiable is when none of the A's and B's, I mean, they're all in conflict and you cannot satisfy them. So that's how you do it. Now, here there is this restriction that one of them has to be the size of the clause has to be greater than 1, because in the case where both the clause is a unit, okay, a clause is said to be unit if it has just one literal. In that case, there is this base case, okay, so which is you can have if it is of opposite polarity, then it is contradiction, okay. So, and that's how so that is in the inference rule, okay. And the single inference rule, yeah, an empty clause is always said to be false, okay. An empty clause is considered to be false, and therefore when you have A and A, two clauses, unit clauses that are conflicting, then you derive a contradiction, okay. Now there is also this thing where if you resolve on this, you may get B or B bar, in which case it'll be the whole thing will be reduced to true. Now with this inference rule, yeah, that's we already said. So with this inference rule, you can devise a simple procedure. So that was the Davis-Putnam strategy, named after these two people who came up with this thing. That the resolution principle itself was invented by Robinson. So the idea is, and the strategy is, given a CNF formula, you repeatedly apply this resolution principle, okay, until either you derive a contradiction, okay, or there are no, this is called an implied, sometimes it's called a resolve. It's also called an implied clause, because whenever this is true, this implies this, okay, so that's why it's called an implied clause. This is true, so will this be, but not the other way around. So you repeatedly apply a resolution until you derive a contradiction, okay, and you keep, yeah, so or you don't add any new implied clauses. No new resolvents are derived, okay. Now, why should this terminate? Because after all, we are starting with some formulas that have finite number of clauses with finite number of literals. Every time you apply a resolution rule, you are eliminating one pair of literals with opposing polarity. So every time it's decreasing. So you cannot keep on generating new resolvents infinitely, for forever, and therefore it has to terminate at some point without generating any new implied clauses. Okay, so that's how you do know. To see an example, so for example, here you have you resolve on this. This usually the thing that appears in opposing polarity is called the pivot variable. So you resolve on that B to get A, okay? And then similarly on these two, you resolve on C to get A bar, and then you get a contradiction. So yeah, I mean, you can see that you can apply that to things that are satisfiable. Then, for the other example, where you have this one. So here you have B and B bar. If you resolve on that, you get C bar, F bar, and E. And then there is one more resolution that is possible with C and C bar. After that, you get A, B, F bar, and E, okay? And after that, no more new, resolvents are possible. And therefore, so then it terminates. And since you did not get a contradiction, that is satisfiable, okay? So that is a resolution principle. So what is the disadvantage of this one? So as you can see, that there will be several different, this is called a resolution graph or a proof, okay? That, proof of showing that it is either unsatisfiable or satisfiable, yeah. Didn't understand your question. Yes. Yes. If yes, yeah. Yeah, but you do one at a time, no? Yeah. So that's what I mean. So there is, take another example. So this one is yeah, you can do that. I mean, for example, here, okay, for example, maybe this will so what, yeah, so here you have, yeah, there is A and E bar. You could resolve it between these two things. So this is A, and A bar appears here as well as here. You can choose either of them to do it. Okay. So that's why, yeah. So does that answer your question? So because see here there is a choice between resolving using these two clauses to resolve. Okay, this is the same thing. It's the same proof. So you resolve on this, and then you do, and then this is another way to derive the contradiction. Does that answer your question? So what is? Yeah, you have. Yes. On A, you get B. Once you resolve two clauses, no. That's the most important thing, okay? You don't eliminate anything, okay? So you will have to keep, because see, in this example, I got a new clause, new resolvent, okay? So you could either, in the previous proof, I was only resolving with, between new clauses. You will have to keep, you can, when I say no more new resolvent, you could resolve it with any of the original clauses or the new clauses. You're as though you're adding, once you resolve, you're adding this to your original set, okay? So you're adding this. Now you start with these set of clauses, okay? Now you resolved using these things. So you got on A and you got B or C. Now your set of clauses is your original set of clauses and the resolvent is added to the thing. Why is it sound to add? Because a resolvent is always implied by your original set. Okay, so whenever this is true, this is also true. So adding that will not change your satisfiability assignment. Yeah, that is right. So you will have the original. So because in this case, you see, now the possible resolvent is between this and your original thing. Okay, so that's how you keep doing. Therefore, when I say that the Davis-Putnam strategy, you will have to keep applying until there are no more new clauses, new resolvents that are possible with whatever with every clause that you've generated until so far and your original set of clauses. Yeah. Certainly, yes. So as I said, the resolvent, consider that as being added to your original, and you could resolve using any clauses among the current set of clauses that are possible. Okay. Second and third. Okay. You get A. Oh, then here you get A or not A. So that is true. Okay. So this goes away. So then you still, yeah. So that doesn't add anything. So after that, you can resolve between these two things. You get once again true. This is on, yeah, this is satisfiable. Okay. When are there any other new thing possible? No, nothing is, I mean, there is B and B bar. Okay. So this one is on A and A bar. This one is on B and B bar. That will also give true. Okay. And you can see. So then you no longer have any thing, because in this case, it's so obviously true, but none of them, when you resolve any of these things, they're all giving just true. They're not adding, they're not giving any new clauses. Okay, so. Okay, this is, I'm sorry, this is A bar. Yeah, it's A or not A, no? So when you resolve this, when you resolve on a particular thing, look at this. You read this carefully. So what you have is, you take the union of the rest of the literals, okay, which is this junction of these things. So when you resolve between B and B bar, okay, I'm sorry, here, so he said between these two things you get true, because what you have is A or A bar. So that is true, correct? Now, if you resolve between these two things, you get A. and you get a bar here. Okay, so here it's not. So here, now you can end up getting a contradiction. It's possible, yes. Okay, there I jumped the gun. So you could get a contradiction. Therefore, this is unsatisfiable. Huh? No. But that is where you're misreading. Okay, you will have to explore, keep resolving until you don't produce any more new resolvents. Okay, just because you did not get you got A and B, there's no contradiction, doesn't mean that there is. So read this thing carefully. Okay, Davis-Putnam logic is keep resolving until no more new clauses are ever produced. Okay, so here after this A and B, you can't conclude anything. You'll have to keep doing it until you have resolved, produced all possible resolvents. And that's why this procedure, while it is a single inference rule, which is amazing in that sense, you keep doing it, you will have to not only keep your original set of clauses. How can you check if you're not getting any more new clauses? You will have to keep all your original set of clauses, keep all the new clauses that you generate, and every time you have to keep checking, if there are possible ways, you've eliminated all possible ways of doing it. Yeah, that's right. That's right. You will have to do. So it's very expensive, both in terms of memory, especially you will have to, so memory usage is very, bad in this case. Okay. Yeah. So I'm going to skip this things. Yeah, there is this notion that it will be useful. Maybe it will come in one of your papers. So, for example, so given a set of clauses, and given an unsatisfying clause, this is a concept, okay, that is useful. If it is unsatisfiable, usually what it means, there is some subset of its clauses that from which you can derive a contradiction. Okay, that's what happened here. You see, these two are satisfiable. Okay, these two clauses together are satisfiable, but these two are not. Okay, now as a whole, this is unsatisfiable. So in this case, you can ask the question: what is the smallest subset of an unsatisfying formula? I mean, unsatisfying set of clauses that the smallest or the minimal set of clauses that makes it is still unsatisfiable. So that kind of gives you the core, okay, as to why it is unsatisfiable. In this case, for example, there are two. Okay, so this is B and B bar, E and E bar. That's a unsatisfying set, as well as this one between two braces. And this happens to be the smallest subset. In this case, it is the smallest. For some formulas, you can get multiple subsets of equal cardinalities. That's why I say a minimal subset. So that is also, for example, Z3, you can try and get these. It also produces a minimal subset. Okay, and it's an expensive proposition because you may end up having to look for lots of different subsets. So it may not guarantee always to produce the smallest one, but it does. So this is a useful concept to keep. So the drawback of the Davis-Putnam strategy is you need to, as I essentially keep and it's memory intensive because you have to keep track in order to check if there's no more new clauses. You have to keep all of them, and then once you produce, it produces a proof of whether it is unsatisfiable or satisfiable. But what is the exact assignment that that the model to extract that you will have to do some extra work. It's very important. Yeah, the order of the variables and the clauses that you pick to actually resolve, it greatly influences the size of your proof. Okay, by size of the proof, I mean, the depth, the number of resolution steps that you have to do to get the contradiction. Okay, so that is left in the Davis-Putnam strategy open. Okay, so it only says as long as you keep doing it, then you do. Now, one of the strategy that you could use is you bias your resolution towards shorter clauses, or in the unit clauses. Okay, for example, here, if there are unit clauses, if one of the clauses in your resolution is a unit clause that has one, I mean, what is the effect of, for example, in this case, resolving between these two, where B is a unit clause? Okay, equivalent to plugging the value of B into this and then simplifying. That's what the effect is. So it's because if it's a unit clause, you will have to assign, it forces an assignment, because if it's a B, you will have to assign it 1. If it's not B, you have to assign it 0. So you might as well choose the unit, a unit first, get rid of all the unit clauses, pick them for resolution. Okay, and that is what is called unit resolution. Okay, so whenever you pick that, I mean, by extending, maybe a strategy, Davis-Putnam strategy, a tweak is you first pick the smallest, the shorter ones of the clauses. Okay, but the most important thing is, later strategies involving resolution were biasing towards this unit resolution, and that's what this strategy of, which is called DPLL. Okay, I mean, resolution is the concept that is used still in modern day solvers, but almost all modern day solvers at the core have DPLL with a whole bunch of heuristics. Okay, yeah. Yeah, the worst case, there's nothing you can do. See, but the surprising thing is SAT solvers, while the worst case is always going to be exponential, they work so well in practice. That is the real surprising thing. Well, I don't know if you call it average. Okay, no, that I don't know if there is, there might be some average complexity. I don't know what the average complexity, etc. is. But what I'm saying is in practice. I mean, that's, I say in practice because maybe of course, the reason for that is what I will tell you. There were 3 breakthroughs, okay, in the last 20 years, okay. That 20 years is now 25 years probably. And that's what I'm going to give you a feeling for. Okay, there were 3 certain breakthroughs in the last 20 years that has made it, SAT solvers, present-day SAT solvers work well in practice. I don't mean the average thing and so on. There is something, maybe there is something in the kind of problems that you get in practice that are, when encoded as into as Boolean satisfiability problem, have some structure, okay, that are make them amenable for these heuristics. Okay, so don't know. That's the thing. Or maybe there are, we are kind of veering off because you asked that question. So that is, maybe there are some islands of tractability in this whole problem. Okay, that, for which there are several islands of problems that are very tractable. Okay, and most of the kinds of things that appear in practice, that are relevant in practice, they're very close to these islands of tractability. Okay, there is that line of research as well. Complexity theory people have studied this a lot and still don't have a complete picture. But it is a fact that certain things, certain breakthroughs have led to, there is this graph, I mean, I have, so until 2001, okay, this DPLL, which I'm going to show you, or some variants of those DPLL with some heuristic were being used, they were able to scale Boolean satisfiability only to maybe tens of thousands of variables. Between 2001 and 2010, okay, the 10-year period, there were three important contributions that immediately scaled the problems. By, I mean, the scale I'm measuring in terms of number of variables and number of clauses. These are the two parameters that are used in determining what the size of the formula is. I mean, this is very relevant when you're applying to DNN, okay? So you can see when you encode them, it is related to the number of neurons, okay? And the number of ReLUs, you know, that are there. So immediately after these three things, you were able to scale it to millions of variables, okay? Today, you know, there's a lot of engineering that goes into building these things that easily few tens of millions of variables you can do it. So that's how I'm okay. So what does this do? Davis-Putnam DPLL, and so it basically uses this unit resolution. Okay, so if you have, you know, when you resolve, you will have to pick one of them to be a unit. Okay, or in other words, what it's saying is you always look at if there is a unit clause, and then you know, plug whatever value that you will have to that it forces for that variable into the rest of the clauses. Okay, and that means that this is what I'm applying. Okay, and of course there is the other case in which if P appears positively, then you will have to plug that thing in, so which makes that clause go to true. So which makes that you will, just like in this case, when you did this true, you know, you can just eliminate you know, that clause. These are the two things. Now, that's what BCP is. BCP stands for Boolean constraint propagation. Okay, so what it involves is repeatedly applying these two rules. Because you can, until I say a fixed point, because until you no longer can apply them. That's what I mean when I say until it's fixed point. Because every time you apply this to, you know, you plug it in, that can in turn make some clause go to true, some clauses go to false. If it goes to false, then of course you know that it is not satisfiable. It can make it go to true, or it can also make some of the existing clause become unit. Okay, in which case you can propagate that further. That's what, okay, I say the Boolean constraint propagation is repeated unit resolution application. Did you get that? Yeah. And I will show an example. So BCP is a repeated application of picking a unit clause, okay, and plugging it in, simplifying it, and keep doing it, okay, until there are no more unit clauses in your. No. There are two ways of saying it. You apply this, either of these two rules is what thing. But this is akin to picking that and then getting rid of that and then plugging in that value in the rest for that variable in all the rest of the clauses and simplifying. Okay, that's what I mean when I say plug it in and simplify. So, which is what is effectively applying these two rules. Okay, and then you have to do that repeatedly until there are no more unit clauses, or you reduce the whole thing to true. That's what it is saying. So when you do this, these are the three possibilities. Either it will reduce to true, then you return true, okay? Or some clause because of this application might reduce to false, in which case it will be false because every clause has to be satisfied. If not, there is a third possibility. There will be some what are called unresolved clauses. They neither reduce to true. Some of the literals may go away. They may reduce to false, but there'll be other literals which are not, and the clause itself is not unit. Okay, that possibility is there as well. So in which case, what DPLL says is you kind of pick one variable, choose a variable and assign it. So that is, these are called implied decisions. This one is an explicit decision, okay? Or it's a forced decision, yeah? So you pick that, you choose either 0 or 1. Now, because you're choosing it, the choice that you make may not be correct, okay? Because that may not lead to a satisfying solution. That's why you will have to do both, okay? So then you recursively apply DPLL by adding the E to it. That is the positive, assuming that you make a choice of making it 1. Then you apply recursively the DPLL to that. And if that returns true, then you have a satisfiable. But that, if that returns false, you still have to look at the other choice, okay? P0. It's choice of, so that's what, this procedure is, okay? It's roughly making it, choosing a variable, making a one decision on it, continue to apply. They keep applying it. It's like a depth first search. And then if once you hit a false, then you will backtrack and then look at the other decision. And that's how you do it. I mean, I've written here as a recursive procedure, but if you really implemented it, you will, there's backtracking here, because in recursion there is backtracking. Okay, and that's what, yeah. So I've only, this one I've already said. So if, at the end of BCP of F, the clauses in your formula can be in one of these states. They can either be satisfied, which means that it simplifies to true, or unresolved, or it can be false. Okay, so look here, it eliminates the disadvantage of resolution proof. In what way? You now don't need to keep track of your new, the resolvents. Okay, you only work on your original set of clauses through repeated unit resolution. Okay, but the price you're paying is that because of the explicit choice that you make here, you will have to do backtracking. Okay, that is, that's a price that you pay. Yeah. So I mean, I'm yeah, I will show an example, but I'll list how present day, modern day SAT solvers, how the variant of DPLL that it uses, how they're different. They are different in these three things. Now, there's no learning, okay? Whenever there is a conflict, whenever something, there's a conflict, some clause reduces to false as a result of applying this unit resolution. Here, you're not learning anything, okay? So we are doing machine learning, but it is not, it is, well, I mean, when you analyze something and learn, something, and you see what it is that you're learning. So it is not like machine learning, but it is learning from proofs, okay, is what that's going on there. So there was no learning, okay, and that's what this extension to CDCL, conflict-driven causal learning, that's what it stands for. CDCL stands for conflict-driven causal learning. In a way, it is learning, okay? So you will see, it may not be in classic machine learning way, but it is learning something new fact, and then it is using that. That is one, okay? And you can see that even with this, when you choose a variable, what order that you choose in matters very significantly, okay? So if you choose something, just like here, the choice of the pivot variable and the clauses that you choose to resolve impact the length of your proof, okay? Here also, how far you need to go down and how many times you have to backtrack, etc. Very much depends on the choice of the variable. So there are lots of heuristics that people, have developed that have been very successful. And then this one always backtracks at the latest level, okay? So it goes, keeps making a whole series of decisions And if it gets a conflict at some level, it only backtracks one level before. Okay, that is called chronological backtracking. And it turns out that if you use this learning technique, then you could jump. Okay, there is value in not doing chronological backtracking, but you could jump several levels and then improve the efficacy of this learning greatly. Okay. Plus, I should add another thing, which there's a lot of how do you do BCP is very important, because if you use DPLL, in any typical SAT solver, 90% of the effort, apparently, this is borne by experiments, okay, is spent in doing this BCP, because you have to repeatedly keep doing it. So a lot of engineering has gone into making BCP, and in that BCP, a lot of time is spent on looking for clauses, plugging it in, and then doing it. So a lot of engineering effort that, I mean, all those BCP requires you to scan all the clauses. So it is already, linear or in a polynomial, but there are techniques, it's an engineering techniques that doing BCP or some components of BCP in constant time, okay? So those kinds of techniques have been developed as well. It's these 4 things that have made present-day, modern-day SAT solvers effective enough to be able to apply to formulas that are in size, which has millions of variables and clauses. And that's why, we're even talking about being up, without any reservation, at least applying it to big neural networks, okay? So what I will do is, I don't think I'll have time. I'll talk about this learning technique, okay? What you learn. First of all, I don't think so. See, when you apply unit resolution, I mean, forget about this concept of unit resolution is like you're making decisions. Either you're making implied decisions that you don't have a choice about, or you're making explicit decisions. Okay, so it is just simplifying the thing. So you're not generating any new clauses here at all. Okay, the original set of clauses in your original formula are just being simplified based on your decisions, right? So no, that's not what it is. Okay, it's not remembering those things. That is not where the thing comes from. I'll show an example and where what exactly is what is the price that you're paying. Okay, you'll see that it learns from conflicts. Whenever there is a conflict, okay, that is when, as long as you're not getting a conflict, there is hope that you're making progress towards a satisfying assignment. Now, when you get a conflict, you'll have to change your decision. There is one of the decisions, the partial set of decisions that you've made for the variables has gone wrong, correct? So you will have to change. So here you say, oh, I will just try something else, okay? Now, where the learning comes from is, can you learn something from your conflict? Can you actually analyze your conflict to see what is the source of the conflict is, okay? And then maybe learn a new fact, okay? Because there must be some reason why that conflict occurs. Can you prevent that conflict by learning a new fact about your original set of formula, and then prevent that conflict? Because if you keep getting the same conflict, if you run into the same conflict is what? Some set of partial assignments. So maybe there are zillions of variables, X, Y, and Z, you make something, okay? As a result of making certain decisions for X, Y, and Z, and then you say W, okay? You make a certain decision which is in conflict with your original decision, okay? So now you could say, oh, if I made those decisions, then W shall not be what you decided for. That can be added as a new fact, okay? And I'll show you through an example. That's what repeated running into the same conflict repeatedly is where a lot of time is spent. Outside of BCP, you keep doing it, then you keep backtracking, and then you go down, backtrack, you down, backtrack, down, and so on. And that is one of the things. So let me show that example. Okay, unless, yeah, you ask the question, I will see if I want to defer it or not. Yeah. Correct. Yes. Exactly right. Yeah. Because BCP is where you keep propagating all the unit clauses until there are no more unit clauses. So when you come here, you already have only a set of unresolved clauses, okay, which are the same set of original clauses, but some of them have got reduced and there's still some unresolved clauses. That's when you choose. Yes. Yeah. There are there are three things. There are two things. Okay, as I told you here, these are two separate things. Here, the decision about choosing the variable, picking the variable to make a decision on, which includes whether you make, which variable you choose, whether you make 0 or 1 for it. Okay, that is this one. What I'm talking about is different. Okay, so there you are actually adding some new clauses. Okay, so I told you the DPLL is great because you don't have to add new clauses. It is kind of doing, picking something from your original resolution, but it's not kind of adding merrily any resolvent, but only things that are required to prevent conflict. Okay, I think an example will be clear. So these two are two separate things, okay? Yeah, this is just the same recursive procedure in a flowchart way, okay? Forget about this, okay? These two are with it's CDCL. So here, you enter Boolean BCP, you keep doing it, okay? Until there's no conflict. And then if there are resolved things, then you decide, and then you keep doing this, okay? And then you have to backtrack, okay? Forget about this right now, okay? This will come in only when that learning part comes, okay? Otherwise, if there is a conflict, then you backtrack, okay? And then if you all backtrack all the way to the top, and then you try to backtrack even beyond that, then of course you have explored all of it, and then you give unsat. And that's just, okay, here is an example. I hope you can see this. This is a set of clauses. So here, when there is a dark, solid edge, I make a decision on that variable to be 1, okay? So here, there are no unit clauses. So BCP will not have any effect, right? Because there's no unit clauses to begin with, okay? So that's the thing. So you'll have to make a explicit decision. So I pick X1 and then make 1 on it. So if I put X1, 1 on it, this goes away, C1, these two things go away, correct? But you still have unresolved clauses. So I pick make X8 to be 1, okay? So 1 means this will reduce to 0. Still, I have still unresolved, okay? Then I make a 0 on X7, okay? A 0 on X7. That triggers a lot of BCP. X8 is already 1, so this has gone away. X7 being a 0 immediately makes X6 forces X6 to be 0, because that's a unit clause. X6, similarly, X7 being a 0 means X5 has to be a 0. okay? So that's what these are the implied decisions, okay, by BCP. And then these two being X6 and X5 being 0 when plugged into this one forces X4 to be 1. X4 being 1 means X3 to be 0. Now X3 being 0 will mean, see, this is already gone. This is 1, okay? So X3 being 0 means this will require X2 to be 0, but this one will require X2 to be 1, okay? Therefore, there's a conflict, and that's this conflict in clause C2. Yeah? Yeah. If I plug X1 has already been eliminated to be 1, therefore this has gone, okay? So the moment X3 becomes 0, when I plug those, X2 is already 1 here because of that, okay? X3 plugging 1 will result in a conflict there. So, and you can see that now DPLL will simply backtrack, okay? You simply backtrack. There's a conflict here. You go back and now you explore something else, yeah? And then you see you will hit the same thing, the same conflict because of X4 being, what is this? This is X6, I think. I mean, once again, you will end up getting the same conflict. I mean, the conflict will be in C2 because the same thing happens. The reason is that the moment you make X1, make a choice on X1 to be 1, these clauses are such that X4 can never be a 1, okay? That's because your original set of clauses implies, F is your original formula, implies this fact, okay? That says that X1 and X4 can never be 1 simultaneously. And that's what was missing here, but that is implied, okay? And now, as soon as you get this conflict, if somehow you could analyze this conflict, the source of that conflict, and then learn that this is the reason that that conflict is happening, and then you add this to it, okay? This is, after all, is an implied clause, okay? It's implied by your original set of clauses. So you will see that this clause you can get with some resolution on your original set of clauses, okay, which is all these things. So here it is, it is selectively using resolution, okay, whenever there is a conflict to learn that thing. So that's why I call, what is resolution? It's a proof. It's a proof of showing that there is a conflict, okay? This is what is being learned. So by looking at that proof, you're learning, that thing, and that's what is happening here. Okay, so you see, this is a very, very important thing. So it is kind of, here you're just resolving, freely, merrily, okay? Whereas there, you're, kind of using only unit resolution and then learning from the, and I just want to show this one. Okay, this is exactly what I said, okay? The source of that conflict was, is kind of explained by the fact that X1 and X4 cannot be 1 simultaneously, because this is a follows. This is an implied clause of your original set of formula. Now, somehow, if after you get the conflict, you can learn this. As here, what I've shown is, hey, look, between C1, C2, and C3, if you resolve those things, you're getting X1, not of X1 or not of X4, okay? But this is going forward. You have to learn from the conflict. You kind of have to go backwards to somehow derive this thing. Okay, so that is what CDCL does. Okay, so I'm going to show you, going back to yeah, this I've shown. Yeah, with CDCL, this is your procedure. Okay, so this is, you start with BCP and you keep doing it until yeah, so there are two things here. I mean, I think it's easier to see the thing. So the analyze conflict and backtrack. Okay, those are the places where it's different. I'm not going to go into a lot of details, but I'm just give you an idea of how you could derive from the conflict, that learn those conflict clauses through an example. Okay, and yeah. So here. So I'll have to, there's a lot of animation, so I'll stay here. Maybe I should move this thing closer to that thing. Maybe that end is better probably. So I think this is kind of the same set of things, okay? I'm going to build something, okay? Here, in addition to doing DPLL, in order to learn from this conflict, I'm going to be building something. This is called something called an implication graph, and you will see what I'm building. And then from that, you can easily learn the conflict clause that can be used to prevent that particular conflict. Okay, so that you won't hit into it, keep hitting into it repeatedly. Okay, so you're starting with the same thing, and now you have to make a explicit decision. Say I make explicit decision X1. This at 1 means I made it at level 1, okay? Because I'm attaching that level to it. So that will, yeah, C1 and C2 get simplified into that. So the red means that gets 0. So still no unit, or you can't, there's no BCP. So I make X8 1 at level 2, that goes away in C6. Then I make X7 to be 0. The moment to do this, now BCP kicks in. Yeah, that's what this thing is. There's a decision, and now decision once again, and then BCP kicks in. What this thing, okay, what I'm building here keeps track of what literals, explicit decisions are forcing decision, an implied decision, okay, in terms of BCP. That's what it is doing, okay? So as a result of this, X5 is an implied decision, yeah? That has to be a 0. Not of X5 means I have to make X5 0 to make not of X5 1. And that also, these two decisions make, when plugged into C6, will make X6, C6 become unit, and therefore it makes it a 0, and so on, okay? And then that's what is making X4, you see? The moment you make this X4 to be 1, everything is conflict, okay? Because you can't have X1 and X4 to be 0. So that makes X3. This is exactly what I showed. I mean, here I'm building this implication graph, and finally you get into a conflict like this. So this shows all the explicit decisions that you have made that have gone into creating that conflict. Okay, that's why this is called an implication graph. Okay. Okay, so that's just a conflict. I'm just denoting that there is a conflict when these decisions are plugged into yeah. So when all these either set of some set of explicitly made decisions and implied decisions through BCP end up when plugged into C2 creates a conflict. K is a conflict node. Okay. Now you can see that with this conflict, all these decisions were involved in creating that conflict. Okay. So that's why this implication graph among all, you could say, you might have made, this is usually called a partial implication graph, because among all the decisions, explicit and implicit decisions you made, it kind of focuses your attention to that subset of your entire proof tree that is responsible for creating this conflict. Now you could focus your attention on this and try to learn a clause that can be added to it, to this original set of clauses, so that this particular kind of conflict will not reoccur again in your search process. Okay. And that's why you're learning that from the conflict. And that's the learning aspect of it. So, and what it does is this analyze conflict will just, as you do this, this implication graph is constructed, and analyze conflict analyzes this and then picks one of the things. In this case, it says that X1 and X4 cannot be simultaneously one. And that is actually added to at this point before you continue. And then you backtrack, change decisions and so on. So that repeated, that is one. Okay. So how does and then you analyze conflict, and then what it says is, rather than backtracking only one level, that is the other chronological backtracking, it doesn't do chronological backtracking, but rather it says you skip level, you look at these. That's why I was maintaining, no, I'm not, so you look at this conflict. How do you generate this conflict clause is one thing, okay? But certainly this conflict clause it prevents you could kind of read this implication graph, okay? Firstly, these three decisions are creating the conflict, okay? So you cannot have X1 being 1, X2 being 1, and X3 being 0. So your conflict clause is the negation of the conjunction of these things. So X1, not of X1, not of X2 and X3. So that's what it inhibits your thing. Or it can also be this one, X1 or X4, and that's what is being added here. Similarly, you can go back in this thing. So in a way, every cut of this implication graph, cut is a technical graph, defines one conflict that can conflict clause that can prevent this. Yeah. Yeah, that is right. That's why that is useless. Okay. You have to learn something which is closer to this, closer to your roots. Okay. And this one has a nice property that it is also the shortest one. Okay. And, those are the things. Either you could, and that's what is shown here. I'll skip all these things and I'll show you. Yeah. This implication graph is being used to analyze the conflict. Yes. Yes. And like I said, every cut of this thing, the cut is one where this implication graph is completely made into two partitions, okay? Unconnected into this. A cut is getting rid of set of edges that makes this into two partitions, into two independent, unconnected subcomponents of a graph, one involving the conflict node and the other not conflict node. And when you do that, every such thing that you get in the nodes that are the sink of these edges will form a conflict clause. Okay, so you could add this one, x1, x4, or x1, x8, x7, okay, which is the original decision. Yeah, because these are the new facts that you can learn, and this happens to be the smallest one, and that's why sometimes some SAT solvers add all of them, but no longer. Okay, usually most of them add this smallest one, and the smallest one is usually defined as an explicit decision with a unique implication point. Okay, because you look at this one, all paths from the root to your conflict node pass through this x4. Okay, and so in that sense, this kind of covers all these things, and that's why it's called a unique implication point. So a conflict clause that contains just the unique implication point is usually the shortest one, and they add that. Okay. Of course, there is thing. I mean, I've shown this in as analyzing, constructing the implication graph, but constructing the implication graph itself is quite expensive. So there is another way to do it using resolution. Okay, without actually constructing the graph, because that can be take a lot of memory. But I'm not going to show that, okay, in the interest of time. But it is possible to just keep track of all the decisions that are made, sequence of decisions, and then use resolution in a backward way to do it. Okay, so that yeah, and that's what this thing is saying. Okay, the one that has unique implication point. Okay, so what else do I want to say? So you get the idea now. So yes, if you look at in Z3 also, you could, I don't know, there might be ways in which, I mean, as you go deeper and deeper into the thing, there'll be more and more conflict clauses that you'll be generating. And sometimes you may end up generating so many conflict clauses that could, you will see sometimes that if you're not getting any solutions and your Z3 is getting very sluggish, it's one of the reasons is because it is accumulating lots of conflict clauses. So there is a feature in Z3 or in any SAT solvers where you could do just restart. Okay, then it will flush away all your conflict clauses. It's okay to flush your conflict clauses with all the ones that are generated because they're all implied from your original set. Okay, but just eliminating them is not unsound at all. So you restart it. Okay, because you always change the decisions. Therefore, you can get good result using that. Okay, so I'll just skip all these things. Yeah, this set of slides also tells you how you could derive those conflict clauses using resolution and so on. So if some of you are interested, you could go through that. I mean, if it is relevant for you, but I'm not, I don't expect to go into that level of detail. But what I want to do is say a few words in the time that I have about how some heuristics, okay, that are used. And one such thing is called variable state independent decaying sum, VSIDS, and that's what is used in Z3. Okay, this is a patented technology, patented idea that was, I think was developed at a group that does a lot of research in SAT solving at Princeton. And the person that invented it went and joined Microsoft, and now it is part of Z3 and the other things. So what would be, how would you do it? Okay, I mean, if you were to have an idea, okay, which variable would you pick? to make an explicit decision. Given a set of clauses in your original formula, that's correct, okay? Yeah, so you count the number of times a particular thing, a variable appears. And whether you make a choice of 1 or 0 depends on how many times it appears negatively. If it appears more negatively, then you would want to do. You want to simplify it, right, to true. So get rid of clauses. That is certainly one thing. And that's what I meant. And then additionally, the number is one important. And how many times, if it appears more number of times in shorter clauses, then it is even better, correct? Okay, so there could be something, and that's what these dynamic largest individual sum heuristic does, okay? It kind of counts the number of times a particular thing appears, and it is weighted a little bit on the more times it appears, that variable appears in shorter clauses, it gives more priority to it. But the problem with this thing is, this approach is that it is dynamic. In a sense, as you can see, these clauses, they're dynamic. Okay, every time you make a decision, the state of the clause changes. Therefore, you have to compute this sum. After every BCP, if the state of the thing changes, well, you'll have to recompute that. I think it's expensive, okay? Because you'll have to now go through all the original set of clauses, which could run into millions of clauses, and therefore there is a static version of it also that you make only once, okay? But that doesn't work that well. You just determine the order based on the original set of clauses in the original set of formula, but then that doesn't do. Now this one is kind of a pseudo. It is somewhat static, but it is it is static in the sense you don't need to do it every time that you apply BCP. But and also it has the advantage that it takes into account the new clauses, okay, new conflict clauses that you derive. So what it does is, it does the same kind of thing. It counts the number of things, but not after every BCP, but after every time you add a conflict clause. Okay, so you have a count in every time you add a conflict clause, then you count the thing based on the current thing, and it also biases that the choice of a variable. The more number of times it appears in the conflict clause, it makes you to choose that. It biases towards the number of times it occurs in the conflict clause. Okay, therefore, that there was one order of magnitude. That is why that's significant. This decision is most all these present-day SAT solvers use this. It was clearly one order of magnitude speed up that they got based on that. Okay, and this is what the description is. Yeah, you have a counter that gives the number of times each variable in each polarity, okay, that it appears. So when a clause is added, the counters are updated only then, okay, not every time BCP is done. So therefore, whenever there is a conflict and then you add a clause, then you recompute those things. The unassigned variable with the highest counter is chosen. All clauses are considered to determine and not just the unresolved clauses. And sometimes you in order to bias it towards the conflict, the number of times it appears in conflict clauses, all the counters are divided by a constant, okay? Because the more, if you divide by a constant, the more recent clauses in which they appear, will get higher priority, and that's what this this thing does. And finally, this is just, I'm going to mention this. Yeah, normally you keep counters. How do you update the counters? You will have to count, when you make a decision, you have to count the number of clauses, in which it appears, right? So, but that will require you to scan all the clauses, correct? Okay. But here is, okay, so it takes order n, where n is the number of clauses. But there is a very interesting idea, clever idea, where you only need to keep a watch on 2 clauses. You don't need to scan all the clauses, only 2 clauses. And those are called watched, put literals in each of the clause. And then you could determine which clause becomes unit. See, whenever you make a decision, in order to do BCP, you will have to find out which clauses become unit, right? So that's how you propagate. And that's where most of the cause. I told you that BCP takes 90% of the effort. So the time that you require to check which of the clauses in your original formula becomes unit is very critically important. That you could do order n, which complexity-wise it is very efficient, but it is not, okay? It is, in practice, that will take a lot of time, because then we are talking about, you want to scale it to millions of variables. Whereas here, it is a technique that can actually, you can do that in constant time, regardless of the number of things. So that's a very important engineering thing that is done. So that's that. And the final thing is this backtracking. Okay, this backtracking is, so instead of doing chronological backtracking, what you do is, okay, that's my last point, and I'll let you go. Yeah, so what it does is it looks at all the literals in the conflict clause, okay? And each of these things, it picks backtrack to that level other than the most recent one. Among all the literals, it picks that literal whose choice was made the earliest. In this case, X4 was, where was it? Okay. Okay. So this is, if this is the conflict clause, this one is the current decision level, okay, that created the BCP. So the only literal that appears other than this current level is at level 1. So it backtracks to the earliest level among all the latest level among all the literals that appear in that. Okay, so if this was the thing, conflict clause that you added, then it would have backtracked. Even in that case, it would, the earliest one, it would have backtracked to 3. Okay, that's the idea as to why that will give you most effective thing is because, I mean, apparently there's no thing. I mean, why? There are 2 things. One is because that was the earliest decision that was involved in creating this conflict. I mean, the latest decision among all the decisions in the conflict clause that was involved in creating this conflict. With the new thing that you learn, you might as well do, because in all the decisions between that and this were not germane to the current conflict. Therefore, you get more oomph in for the clause that you learn by backtracking to that level. That is the heuristic idea. That's really only a heuristic. Okay, both the decision as well as this level to backtrack, which is used. You got the idea of how you determine. You look at all the literals in your conflict clause, and then you backtrack to that, the latest one among all the literals, other than the current one, that exists inside that thing, and that's what you backtrack to. So in this case, it is one, and so on. So that seems to work well with the strategy of puts the learning aspect to good use. Okay, so those are the thing. Okay, so I'll end, and thank you for your patience. And tomorrow we're having a special class. Okay. Yeah, go ahead, please. I mean, and I'm going to be, the topic will be simplex. I don't know how many of you, I'm going to be describing the simplex the algorithm, okay? Because which is very crucial for our, for DNN verification. The simplex, and then its extension that is, that I will do in the next class. So if people, yeah, I mean, I encourage people to show up, but especially if you have not, seen, if you're not heard the simplex algorithm, so that's what I'm going to be describing tomorrow. And the class tomorrow is at 5 o'clock. Okay, I will record it, and then that will be online. Yes. Why you prefer offline? I mean, oh yeah, I meant online because given all this mess, okay, probably offline is better. But is there any preference for online? No. I'm sorry. Offline is in person. Okay. So I was thinking online. Okay. But if you want offline, I don't mind coming here. Okay. Because it's the same thing. I have to make Shankar come here, and I hope I will restart my computer and be ready. So hopefully that should not. No, but I'll leave the choice to you. I mean, I can come even if one person is here is going to be in prefers offline. I'll come. I'm willing to come. Okay, and yeah, but anyway, I mean, I will be. It'll be there on Zoom as well, so you could join online. Hybrid, yeah. So how many people will come if I show up here? Offline. Okay, so then I'll come here. Yeah, okay.